Hi, everyone, and thank you so much for being here today. My name is Jarrad Wright. I'm a senior researcher at NREL in the Grid Planning and Analysis Center. I'm one of the many researchers at NREL, as I mentioned in the slide here, looking at transmission and probably more specifically on that transmission planning as a key domain. And would like to share today some of the particular areas that we are focusing on in this space. If I could go to the next slide. I'll cover 5 main areas with a closing out part talking about future directions, but the first 4 will talk to transmission as a priority and why we think transmission is necessarily a priority. Transmission specifically at NREL, at the National Renewable Energy Lab. I'll go through some case studies, some previous large-scale projects that had asked a few questions of transmission, and more recently a specific study on national transmission planning, but then going into the specific tools that enable us to undertake those studies and actually investigate transmission, the value, the benefits of transmission. I'll talk about a few tools. And then finally, as I was mentioning, I'll talk to future directions and where our research is heading, specifically at NREL in this transmission planning space. So firstly, transmission as a priority. The way that we see transmission when we think about transmission planning and transmission research more generally is we're thinking about what the drivers of change are. We have these 5 areas that we think are key drivers, the biggest 2 being changing resource mix and a growing as well as shifting demand side. It doesn't necessarily negate the others, of course, including extreme events, so weather, as well as aging networks and distributed resources. But those are the 2 key focus areas that we've really been focused on initially and are starting to ask a lot more questions, as you'll see, of the other areas as well, as those start to change the need for transmission and more specifically into regional transmission needs. And the differentiated need for transmission research, although this has been done before, these drivers are changing and they're changing again, and hence the need for research in this particular area with respect to tools, algorithms, and large-scale analysis, particularly in the US. So I'll outline a bit of this further later on in the presentation as we talk to future directions, but I'll try and at least for now talk you through some of these key drivers and then go into those transmission focuses at NREL, as well as then particularly case studies and tools that we've been developing and will continue to develop going forward. So with respect to those 2 large drivers, the first one being electricity demand. I'm just summarizing at the top part of this graphic, annual US electricity load growth that we're expecting, at least for 3 particular scenarios. Large increases are expected by 2050, anywhere between just under 1% per year growth up to 2.7% per year growth. Most of this is driven by data center, so IT growth as well as manufacturing growth at the moment. But we also expect this to be potentially further driven by the electrification of transportation, less so, but also potentially further by sector coupling into industry. So examples of oil and gas, and of course the electrification of a lot of those operations. And then secondly, the changing resource mix. So the bottom right-hand graphic, although we don't necessarily intend for you to read all of the details, that's just a spatial disaggregation of future generation for a particular scenario across the US, where we start to see the supply resources moving from locations where they are right now, where a lot of existing resources are, a lot of natural gas, coal, and nuclear capacity, to where a lot of the wind and solar, as well as the battery storage that goes with that in some of these future scenarios are located, which necessitates an increased need for large-scale transmission. So of those 2, post large-scale industrialization, I just wanted to talk here to transmission infrastructure aging, but post large-scale industrialization driven by World War I and World War II, and of course, the post-World War economic boom was driven by this large-scale infrastructure expansion. So you'll see that just in the transmission networks, for example, between 1946 and 1949. This continued further towards 1960 as more transmission networks were expanded and meshed in the East as well as in the West. And this is one of the biggest growth periods in US history that was realized. Transmission network modernization since then has been surging in particular periods for rebuilding. Otherwise, with the exception in more recent years of the Texas Competitive Renewable Energy Zones, the CREZ zones, in 2013, large-scale transmission expansion, as you'll see in the top graphic on the right-hand side of the slide that you're seeing now, has generally speaking been stagnating or declining over the years. So what I mean by large-scale transmission is transmission above 230 kV towards the 345, 500 kV and above that. And a big transmission that then needs to be met as a result of this with big answers at scale is The quick deployment of large-scale transmission is possible. I just demonstrated that through previous examples of how transmission was built out, and the need for increased transmission infrastructure as a result of aging existing transmission, as well as some of these drivers for change, as I was just mentioning on the supply side and the demand side, really means that there's a big challenge to be met. It has been done before, but quick deployment of large-scale interregional transmission is really possible. So as one of the third drivers, though, specifically on weather and extreme events, the growth of large-scale disaster events that impact bulk power systems broadly has also been growing in number since the early 2000s, particularly severe storms. Although the cost of these events is also showing an upward trend, but with less strength in that signal. Power system operators have been following the weather from the very beginning, though. They've had to in order to understand load patterns, the impacts of floods and droughts on hydro plants, as well as ambient temperatures on thermal plant operating characteristics. But with the adoption of increased amounts of wind and solar, particularly these variable renewable energy technologies, are very dependent on the weather, of course, and that becomes then more complex for system operators and planners to plan around. And with large-scale transmission, as you can see for the example shown here from 2007, with large-scale transmission, there is the potential then to move large volumes of energy across long distances from areas not impacted by potential severe weather into areas where it's needed. And this is another driver of some of our research, particularly in transmission at NREL. But if I just take a step back from being a researcher and diving into the weeds of some of these drivers, particularly in the US, I thought it might be useful to take a step back and think about the general public interest in transmission planning. And just using a very informal Google Trends analysis, the general public interest has grown quite substantively just in the last 4 years. Before that, generally speaking, quite flat, actually slightly negative, but since then growing at above 20%. So this is formalized by policy direction, summarized inclusive of potential actions and achievements in the next slide from a federal level. And I'll talk through some of those specific details as I then go further into transmission at NREL following that. But initially, just across the three main areas of financing, at least at a federal level, supply chain and permitting, the intention is not necessarily to read all of this text. You'll have these slides afterwards as a reference following the session today, but to instead highlight particular programs and some of their achievements thus far. On the supply chain side, following financing, you'll see that supply chain is being addressed through tax credits. In terms of financing, there's been billions of dollars in public and private sector funds invested up to this year. The listed programs, as well as all of their acronyms, are listed there in each of these three areas of focus. But with respect to permitting, finally, there's 4 areas in permitting reform that have supported and continue to support the deployment of clean energy infrastructure, and particularly there with respect to transmission. So examples of the national interest electric transmission corridors, areas in financing on the transmission facilitation program, and of course, qualifying advanced energy tax credits in the supply chain are just some examples of these. As I mentioned, I don't necessarily intend for you to read all of this information, but I just wanted to provide a brief summary here. You could also have this information as reference following the session today. What I actually wanted to talk a bit more about is transmission at NREL, and then those case studies and tools. So I'll spend most of the time here over the next few minutes. Specifically, NREL considers transmission from multiple perspectives. Our research spans many topics. Those are listed over there. There's probably more, but I've tried to summarize them across planning and operations, the interactions and increasing interactions between electricity and gas markets, test beds at scale for hardware, so all the way up towards megawatt scale type of test beds to test transmission interfaces, utility scale, inverter-based resources, so those dynamic interactions, cyber resilience, and of course then the interaction between transmission systems and distribution systems, as I was talking about previously on demand, distributed energy resources is something that's becoming increasingly important. And as we take a step back from that again, also the broader impacts on the economy. But how we do this specifically at NREL is through these transmission planning models. We try to integrate data and expertise across the entire institution, across NREL, for this impactful, integrated and multi-model types of assessments. And I'll talk to a few examples of that in the next few slides when I go through those case studies. But I thought at least for now, particularly in the Grid Planning and Analysis Center and across a few of our other colleagues, the Power Systems Engineering Center and elsewhere, what we aim to answer is the important transmission policy, economic, deployment, and engineering questions. And I've just listed those across 3 main areas here, at least in terms of our focus at the moment. And the first one is on interregional and national multi-valley transmission planning. So the potential for high voltage DC, the value that that could potentially provide, multi-terminal as well as meshed operations of high voltage DC, grid enhancing technologies, and of course transmission upgrades, so the potential for reconductoring, and of course then project level types of constraints. So if there is insights that we can provide and tools that we can provide with respect to siting, supply chain, as I was mentioning, corridor limits, it's really where we want to be focusing to support industry on better understanding and getting things moving quicker in terms of transmission deployment. And secondly, on integrated workflows, this is where we're trying to link a lot of tools together to better understand all the way from the beginning towards the end, from the fundamentals of the capacity expansion outcomes towards production cost and power flow modeling, as well as all of the dynamics and then the economics go with that, to quickly and replicably assess economic viability for major opportunities. And this can go all the way from national scale down to states, potentially even locales, with respect to their decision making and how those link together. And then finally, on interconnection studies, of course, this is an area of focus by the DOE. NREL is contributing to a range of studies in that space, but our focus as well is to then improve interconnection study workflows, potentially apply new algorithms in that space to make those more efficient, turn projects around quicker, and allow for interconnection queues to be managed more efficiently and forward. So the methods and the data to address these queue challenges. And I just wanted to briefly mention here industry linkages across three main areas. The first one is collaborations on large projects. So collaborating with independent system operators and regional transmission operators, RTOs, as well as developers and academia and subject matter experts in industry on these large projects. We often, or actually always, have these members on our technical review committees in our subcommittees to make sure that, number one, we improve the quality of our research, but number two, we also help to address the real world challenges and actually attach our projects to what industry challenges are and what industries is facing at the moment. And then secondly, in professional organizations, a lot of our staff are part of the very well-known institutions, particularly in the US, IEEE, as well as ESIG. We contribute to various working groups, as well as CGRA internationally, and a range of others that I won't necessarily mention today. But then in terms of research partnerships with utilities, governments, other entities, we have various research partnerships and arrangements all the way from the actual underlying modeling and emulation and workflows that enable you to then undertake transmission planning, but also towards that hardware that I was mentioning previously. We have a large test facilities at NREL and various facilities that are not necessarily directly linked to our South Table Mountain campus, but at the Flatirons campus, as an example, is one of those. So I've spoken a little bit about transmission at NREL and our linkages, but I think I'll talk a bit more towards case studies and tools next. I've got 3 examples here of some continental US-wide studies that had been done in the past and one very recently. And then some of the tools that enabled that and some of the tools that were built out of that I'll also outline. So particularly the first one is the North American Renewable Energy Integration Study. I think a number of people that are on this call are probably well aware of that. You can link to that in the bottom left there, but I think informing stakeholders on various key issues at the time was really important with respect to ramping of thermal and hydropower and storage during the day versus the night, transmission, particularly in this case for NARIS, enabling the sharing of diverse resources between regions, understanding and better interpreting curtailment, how that happens, when that happens, during the day, during the evenings, during particular months of the year. And then of course, imports and exports from the region, particularly in this case, imports and exports, at least exchanges between the US and Canada during sunset and sunrise hours was a particular insight. And if you're looking at the graphics on the right-hand side, you'll see some of those scenarios that were characterized. International transmission expansion provides 10 to 30 billion in benefits in high renewables types of scenarios. And interregional transmission expansion provides even further benefits, so in the order of 60 to 180 billion dollars. These are, of course, all net present value numbers that I'm mentioning at the moment. And of course, macrogrid benefits are slightly less than that and less than the model optimal build out, but there are additional benefits that we don't necessarily see in some of the modeling tools that were deployed as part of this particular study. The final thing that I just wanted to mention here is a range of tools that were developed as part of NARIS. So the results of these modeling were made public, over 40 scenarios. We established 5-minute wind resource data, including Canada and Mexico in terms of spatial extent. And of course, we also developed the first starting point of another tool that I'll mention a bit later, and was actually part of one of our previous Powered by sessions, which is PRAS, an open source resource adequacy tool. So as a second of the three examples, this was also very recently published, the Atlantic Offshore Wind Transmission Study. And this was an analysis of offshore wind transmission deployment and needs through 2050, where up to 85 gigawatts of offshore wind was deployed in the Atlantic, of course, whilst respecting sort of environmental boundaries and ocean co-use. But in terms of the Atlantic Offshore Wind Transmission Study, they evaluated four main network topologies: an intra-regional topology, an inter-regional topology, one that is a bit of a mix of both, where it's inter and intra-regional, as well as then a backbone type of topology. And offshore wind energy development provides a unique opportunity to add transmission capacity offshore, which can provide value to the onshore grid. Because the grid in the Atlantic regions, as some of you may be aware, is very heavily congested, high demand, high renewables type of 2050 future. This offshore transmission infrastructure can be leveraged by interlinking platforms to then reduce overall system costs. And the interregional topology is specifically designed to leverage those opportunities and connect these diverse regions by interlinking the actual offshore platforms. So effectively acting as an offshore transmission network, in addition to getting offshore wind resources onshore into these load centers. And the benefits of networking these offshore transmissions comes from reduced curtailment, from reduced usage of high cost resources, and of course, contributing to reliability. And the total economic value in 2050 for each of these transmission topologies was compared to a radial topology, and the breakdown of the value by category was then also established. And you can read a bit more about those details in the study itself. But building this offshore transmission, and this is one of the key final findings, is building of this offshore transmission in phases can help reduce development risk, of course, but early implementation of HVDC technology standards is really essential for future interoperability. For example, the interoperable and multi-terminal high voltage DC capable technologies need to be assumed upfront, and those should be available and implemented as a start as you start to deploy this, as you get towards the 30, 50, and then eventually 85 gigawatts of offshore wind that were part of some of these scenarios. And then one of the final case studies, which interestingly enough was actually published last week, it was the National Transmission Planning Study, where we showed that interregionally onshore, transmission can provide benefits such as lowering of emissions, significant cost savings, and of course supporting reliability whilst doing that in some of these highly decarbonized future systems. The maps on the right-hand side is just a nodal realization of one of those scenarios, particularly what's called an AEC scenario. When you read the study, if you click on that link on the bottom right, but you'll see a large amount of wind and solar being deployed in various locations in the east and west, as well as in the ERCOT in the Texas interconnect. And what we found is 6 principal findings. They listed there on the left-hand side, but as I was just thinking about that, you can access those plus 22 supporting key takeaways when you go to the actual study. For now, though, what I wanted to just show is that the increased deployment of transmission with respect to or relative to a limited expansion between transmission planning regions can result in anywhere between 270 to 490 billion in NPV of savings compared to that limited scenario. So although that's necessarily one particular takeaway, we found 6 principal findings between the transmission expansion, the benefits of transmission, the volumes of transmission, the grid reliability as we go all the way through from capacity expansion into nodal production cost as well as power flow, and establish some promising interregional transmission candidates. And then of course, as part of this, we've also advanced a lot of planning approaches and have established a starting point for a zonal to nodal translation at a CONUS-wide scale as part of this study. So talking about what we did as part of these studies, some of the tools that were developed, one of them was not necessarily a new tool, but an innovation of linking tools together. So coupling the capacity expansion and RA or resource adequacy aspects together was an outcome of the National Transmission Planning Study of NTP. And more specifically, we took the outcomes from the capacity expansion modeling tool called REEDS, 134 zones, and establishes the co-optimization of generation, transmission, and storage to meet a particular demand forecast. And we linked that to a resource adequacy tool, to PRAS, where we disaggregate this capacity into individual units in each of these zones. We apply hourly failure and recovery probabilities to establish the system design. And then we actually undertake multi-year chronological hourly dispatch with these probabilistic outages to cover many samples, so a Monte Carlo approach, and taking that information in terms of unserved energy that we see, and actually taking the stress periods when we see those across, in this particular case, those many weather years that you see on the right-hand side. We see that as stress periods, So we identify those days with the highest risk of unserved energy, and then we include those in reads to then potentially build out further capacity and loop between these. So as part of this overall integrated exercise with capacity expansion and RA pool together, we're able to then establish resource adequate systems in one step and not necessarily have to do that in parallel steps or as an outcome of a planning reserve margin, as has been classically the case in previous capacity expansion modeling tools typically. So as a second example after this, I was just mentioning that iteration, but as a second example after this, we also built a set of workflows that link from these capacity expansion outcomes and RA outcomes into the nodal models that we then expand transmission with and have done some transmission expansion planning with. More specifically, what I mean here is we have these inputs coming from reads, where we then build a tool that then disaggregates this down spatially by technology and by region into a nodal network model of the Eastern Interconnect, the Western Interconnect, as well as the Texas Interconnection. We also establish regional interfaces on that basis. So essentially the grouping of individual branches between each of these transmission planning regions, and use that to then build a nodal production cost model, a set of nodal production cost models. And here we'd undertake a performance assessment where we have various transmission constraints, but we increasingly improve the representation of transmission. We've developed a range of tools as part of this to then also visualize this information in grid sight, is what it's called. There's some standardized ways in which we are plotting interface flows and stacks to gain some of those operational supply and demand balancing insights. But what's actually the most important part of this workflow is then the step that comes next, which is when we take the snapshots from this production cost modeling outcome or these set of production cost modeling outcomes and pull them into a linearized interactive transmission expansion prototype, which in this case leverages PSSE as an industry tool, as well as QGIS as an open source geospatial tool. We iteratively and interactively expand the transmission on the basis of the production cost modeling outcomes in order to find out where is transmission overloaded, where do we need to add transmission, as well as doing that for steady state type of conditions or system intact types of conditions. We also do that for contingencies, at least for contingencies that cross each of these interfaces and one primary bus back from that. But on the basis of that expansion, we're now able to take that information, the expanded transmission, feed it back into the nodal production cost, and take that optimality, bind the transmission constraints between the regions, and assess the transmission performance following that, as well as curtailment, as well as the supply-demand balance, the potential for unserved energy as well at this stage. And we can iteratively move back into that green block on the right-hand side, back into the orange block, back into the green block, as many times as necessary to then find out what is the optimal transmission expansion for this particular scenario. So going from that capacity expansion all the way through to the nodal reliability models in production cost, as well as in power flow and contingency. And taking one final step as we move from the steady state towards dynamics, I thought it would be important to just mention briefly as more and more wind and solar, of course, are added, these resources interface with the power grid through their inverters, through IBRs. And traditionally, the analyses in this particular domain would range from phasor-based types of simulations for electromechanical and thermodynamic types of phenomena. In niche applications, waveform analysis would be undertaken for example, for insulation coordination or when specific concerns are raised with respect to stability. And this is where your EMT or electromagnetic transient analysis would come in. This would take a lot of effort, take a lot of expertise to set up and do really well. And of course, the computation resources, if you do this at scale, are really quite challenging. So undertaking the necessary level of detail is important, but it's also important to understand what needs to be done with respect to that level of detail. So what we're mentioning on the bottom right-hand side here is just an example of where we take exactly the same types of analyses, but actually use a different type of a tool called Sienna-Dyne, or the dynamics component of Sienna framework, where we employ lossless averaging techniques as well as adaptive time steps to improve the quicker turnaround times, formulate models in this dynamic space that are important, leave the details that aren't necessarily important, and get to very similar results to commercial grade types of tools. So this you can think of as that next step beyond that last graphic on the right-hand side from the previous slide, where we go from the steady state towards contingency and now do the dynamics, and being able to really do that at scale, potentially CONUS wide as part of our next steps. And talking about next steps in terms of future directions, I thought I'll just spend one slide here and then pause for Q&A. But on these future directions, I've sort of divided these into three main areas, but we really want to push the boundaries on what's possible for transmission planning and operations at scale. So large scale modeling being one. Of course, what goes with all of this is data and model management, and then of course, advanced transmission modeling. So on the large scale modeling, what types of tools and methods do industry need? Are there future interregional portfolios that will continually keep coming out of various scenarios? Are we able to, as you would have seen in some of the graphics, are we able to take those node to node types of straight line expansions and actually establish potential routing, improve cost estimates, as well as then increase confidence early on in the process with respect to the amount as well as type of transmission that's needed, at least at an interregional level. Secondly, and then finally on this particular area is on representing extreme events and of course correlated outages, and pulling this type of information into a lot of our planning models is the next steps we'd like to take there. On data and model management, I already spoke to the linkage between capacity expansion and RA, and then some of these workflows that we've been establishing, but we really want to better integrate and create improved bidirectional interfaces and soft linking between a lot of these modeling tools. So can we do that is the question that we have. And then finally, can we regularly update these databases and make them available to whom and how? How often should we be doing that are the types of questions that we want to be answering next. And then finally on advanced transmission, speaking specifically to offshore transmission options, Atlantic was the one that I gave, the Atlantic Offshore Wind Transmission Study. This is the Western Offshore Wind Transmission Study. There's probably going to be further, but how can offshore transmission options be better integrated into our existing planning models consistently? Considering the challenges of building out transmission as well, we're thinking very actively about grid enhancing technologies, particularly dynamic line ratings and reconductoring, and how do we represent those better, if at all, or should we be representing them better in planning models in that planning domain versus in that operations planning and operations domain. And then finally, what is that role of transmission and resource adequacy? And can you, as a system operator or an RTO, be able to trust those resources outside of your footprint via transmission to provide you that resource adequacy benefit when it's needed the most during those extreme weather type of events? So I'm going to stop there for now, and I'm happy to take questions. I think I'll hand it back over to Tim. Thank you. Tim, are you there?
Thank you very much. That was a wonderful presentation, Jarrad. My apologies on that. Again, we're using the Q&A function at the bottom of your Zoom panel for questions today. I don't see any in there yet, but maybe folks are still percolating here. And as they are, how about I have a couple of general questions. Maybe you could speak to a little bit more, especially with the NTP study coming in. Oh, actually, we just got our first one. Let's see. Are there data for the transmission maps that you showed earlier, as shapefiles or otherwise, available at any of our websites?
Yeah, sure. So this is where we're heading to next, is how do we disseminate this information better? At the moment, we do only have the reports that are out there. The data to support that is what we're planning to disseminate next. So yes, we'd like to be able to share as much as possible that information. There's always the challenge of how we share that. And the data that we are using up front is CEII protected information. So we need to think about that quite actively as one of the national labs. But I think generally in terms of the expansions, those are not CEII and they are just node to node expansions. So we can consider those as something that we'd like to publish and make those available. We'd be happy to sort of discuss that offline as well if there's some specific requests in particular areas that you'd like to consider the data in more detail. Happy to provide that.
Thank you, Jarrad. Let's see. Next, we've got, could you please speak to a little bit more on the bidirectional interfaces and what that entails?
Bidirectional interfaces between models, yes, sure. So as part of NTP, what we started to realize quite early on, and hence we built it into the design, NTP, National Transmission Planning Study. But what we started to realize very early on was that the capacity expansion outcomes at a zonal level are not capturing and will not ever be able to, well, we don't think they will be able to capture the necessarily detailed and complex physics that come with the nodal network modeling. So what we do as part of that is we undertake a range of capacity expansions in a first round. We look at particular scenarios with respect to expansion capacity between regions and can actually feed that information back once we've started to run the first versions of those nodal production cost models, as well as the the power flow and contingency analyses, feed that information back in terms of feasibility of, for example, an 80 gigawatt corridor between two areas as not necessarily being at all feasible, just with respect to the nodal complexity. You get large loop flows, you just don't have the physical space between regions. You only really get to that detail when you get to the nodal. So the first one is that unidirectional feeding back to the capacity expansion. But of course, that capacity expansion also has constraints that then feed into the power flow. So that's the bidirectional part, is capacity expansion. We feed into the production cost and the power flow. Findings from the nodal models, so production cost and power flow, we can also then feed back into the capacity expansion, update those assumptions in whatever way is appropriate, and then be able to rerun those scenarios to establish something closer towards that nodal expansion that we realized in the nodal world versus in the zonal capacity expansion world. So hopefully that answers the question on the bidirectional nature of the models and how they link to each other, but that's at least how we've applied it for now on NTP, and we'd want to improve that going forward.
All right. Next up, how do you account for permitting restrictions with when spatially modeling transmission? Is that an area of focus at NREL?
Yeah, it is most definitely. We have entire teams that are in geospatial data science directorate, and they're able to and have been actively considering permitting, considering potential delays, as well as, of course, exclusion areas. But I think more importantly, what they establish is the friction between building out transmission and being able to establish least cost paths on that basis. That's a next step. That's what we want to be improving on. As you saw in some of the maps that were shared, for example, from NTP, as well as from NARIS and previous studies, those are node-to-node expansions, and we want to better be able to inform particular transmission siting considerations and then enable those to be included in the modeling environments. As a starting point, at least for now, for the capacity expansion, we do assume that only a certain amount of transmission can be built out in earlier years, following which the assumption is, at least when you get towards 2035 and beyond, that permitting challenges have been resolved, that you're able to deploy transmission at particular rates per year, terawatt miles per year, and hence can expand in particular scenarios a certain amount of transmission. In other scenarios that are the corollary to that, where we limit it intentionally, those remain in place, and now we're able to establish that difference between them and the relative benefits between the scenarios.
All right. Right now, I'm not seeing any other questions, but I do have one regarding the NTP study. So what are some of the biggest hurdles we're seeing in the US when it comes to implementing interregional transmission? And how, what are some of the ways NTP is highlighting as having potential to overcome those hurdles?
Yeah, sure. So FERC Order 1000 intentionally tried to address, or is trying to address, the need for regional planning, but that regional planning is happening at that FERC 1000 region level. So examples of PJM, SPP, MISO, etc. Within those FERC 1000 planning regions, a lot of that transmission planning is done with respect to meeting reliability needs, but at the seams has always been the challenge, and that's where NTP tried to address a few open questions with respect to the ability to then look beyond the footprint that you're planning in as a transmission planner and establish those interregional transmission needs across various types of futures that we're expecting to see as a function of current administration policy, potentially future more accelerated policy positions on the clean electricity needs, as well as state-specific goals. As a function of that, NTP tried to then address, well, how much is needed between each of these regions. There are only selected examples of existing joint transmission interconnection queue management and planning exercises that are happening, but CONUS-wide, what is this volume, how much, which technologies across the interconnects, so all of the interconnects, all three, what does that necessarily look like in a consistent manner? And maybe not necessarily the quantitative map that you saw, so the node-to-node expansions, the 500 kV, the 765, the potential for high voltage DC, but the actual underlying workflows and the tools that came from NTP is where we think most of the value will likely come from. Is that we'd like to disseminate that, make all of those tools, of which some of them are already open source, make the rest of them open source, make the data as much as possible available so that industry can then use it going forward to improve the way that they're potentially doing this interregional transmission planning and not necessarily the planning within their specific footprint.
All right, we got a couple more questions coming in now. This one's asking about the scale of the PSSE simulation for contingency. Is that for the whole transmission model for the continental US?
Yeah, so we know that would take a very long time, and we'd probably still be sitting here waiting for results if we started that. So what we have done in terms of contingency analysis is we've intentionally focused on the interregional interfaces. I think I mentioned this previously and quite briefly, so I'll try and explain it a bit more now. Is between each of the interfaces of each of these FERC 1000 planning regions that I was previously describing, we took some of the bigger ones and we also broke them down further. So for example, the SPP and MISO types of footprints, as well as West Connect and Northern Grid. But we broke those down a bit further. And for each of the branches that are crossing each of those planning regions, those are the contingency sets that we considered, as well as then one primary bus back from that for the contingency analysis. So what we're trying to address there is the interregional contingency performance, not necessarily the entire CONUS-wide performance with respect to contingency. So we focused in on the interregional need, assuming then that the intra-regional need with respect to contingency analysis would necessarily be met by the transmission planners within each of those regions who do that on a continuous and periodic basis.
And this next one is asking about the models and software we use. Are they all public domain? And how can interested stakeholders, access some of the tools that we've talked about today?
Sure. So a selection of them are open source and public domain. READS is open source. Sienna is open source. PRAS is open source. So READS being the capacity expansion, Sienna being the production cost, PRAS being the RA or resource adequacy tool is open source. The dynamics tool, Sienna Dyne, is also open source. The tools that were used as part of the specific workflow that I was highlighting in NTP, the one is called R2X, or the ability to take reads and translate it into anything, is also currently being open sourced and will be made available. The challenge with all of this is, of course, you need to feed these models data. So that's always the challenge, but the tools themselves, almost all of them are open source with the exception of the one, which is the power flow engine that we were using, and that's PSSE. Primary reason for using that is industry uses PSSE quite a lot in most regions. So we went with that as the particular power flow engine, but there's no particular reason to have to use PSSE as your power flow engine. You could use anything that has the ability to do steady state power flow analyses, linear power flow analyses, as well as contingency analysis.
Right. Would you be able to expand a little bit more on some of the areas we're seeing biggest needs for new transmission in the US?
Sure. So if you see a lot of the social media posts in recent days, you can follow NTP, and there's a lot of detail being provided there. But I would say, generally speaking, large amounts of transmission, just in terms of quantity, is consistently being seen between MISO and SPP. So getting a lot of the wind from the SPP footprint across into MISO, and then from MISO across into some of the large load centers on the eastern seaboard. So through PJM and down into the southeast, as well as towards Florida. Some of the times there's also a lot of bidirectional exchanges between these interfaces, but generally speaking, lots of power, lots of wind power specifically, needing to be moved from the western part of the eastern interconnect across, and then a lot of the solar in the southeast region being moved up into the load centers. So for example, in the 500 kV networks in the southeast, as well as in the FRCC region. When certain scenarios assume the ability to interconnect the three interconnects via high voltage DC, we see lots of bidirectional power flow between the regions, particularly between the eastern interconnect and the west. The high voltage DC enables a lot of that, but there is a lot of strengthening of the underlying AC systems, particularly in the western interconnect, in the west, where transmission networks are very long and necessarily on a relative basis weaker than in the east, and less interconnected and less meshed. But the supporting high voltage DC between those interconnects enables that bidirectional power flow to move the wind power that's in that SPP footprint across into the west, as well as then when we assume in that high voltage DC example I was just giving, the ability to build high voltage DC, for example, between the ERCOT or the Texas interconnection across into the east as well into the west, is something that is of high value, as we have the ability then to move a lot of the solar and wind power, balanced, of course, with lots of storage that goes with that in the existing resource mix, across into the west and then back into the Texas interconnect, as well as then across into the east and back into the Texas interconnect. So bidirectional transfers are possible there too. So those are just some of the general trends that we're seeing. Large scale transmission, potentially also the need for voltage uprates in particular areas. So where there's a dominant 345 kV network in SPP and MISO, that's moving more towards 500 kV, potentially even 765 kV. And then in the scenarios where we were considering high voltage DC, that does become a real option to move power long distances towards some of these load centers. But in the scenarios that we had been analyzing, particularly as part of NTP, that's multi-terminal and meshed types of high voltage DC configurations, which there are still a range of open questions there with respect to institutional coordination, as well as then, of course, just the underlying technology. So multi-terminal and meshed high voltage DC operations is something still being actively researched, but at a very high level of technology readiness nonetheless.
All right. This next question, if you are, how are you modeling the ever-increasing timelines for interconnection requests to be processed?
Specifically for NTP, I know I'm not answering those questions, but we didn't necessarily consider that as a binding constraint in the long run. I think I mentioned this a bit previously, but at least initially we have a slower rollout assumed of new resources just because of these challenges with respect to interconnection queue management. There are a few other ongoing projects that are trying to address this. I think there's the DOE I2X roadmap that's continuing. Some of the national labs are part of that too. NREL is also contributing as part of that. It's being led by one of the other labs, but we're also contributing as NREL to that particularly. We know that it's a real challenge. We know that addressing the interconnection queues in various areas is of critical importance, and of course making sure that cluster studies and FERC 1920 and all of these new either regulations or standards that are coming out are also being complied with is something that we're tracking and trying to build out the tools and the capabilities for industry to be able to utilize in future. An example of that is the potential application of AI, specifically large language models, and the ability to sort of feed this information, learn, and then create much improved workflows, more efficient workflows for managing interconnection queues in the various regions. As it is a big challenge, and hence we're trying to address that as part of it. If you remember, one of the previous slides was specifically talking to interconnection queue management.
Right. As we wait for further questions, I have another one for you. Are there any specific examples of interregional transmission that NREL is looking outside of the US that's informing transmission planning analysis?
Not that I am aware of directly. It may be indirectly and through some of our participation, for example, in international working groups. CGRA is one of those, but not that I'm aware of directly. Most of the work that personally I've been involved in, as well as those that I'm aware of, is very much domestic and US focused.
All right. Doesn't look like we have any further questions at the moment. So with that, we can give you guys a little bit of time back today. If you would advance the slide, please. Our next Powered By webinar is going to be Powered by Ochre, and that's going to be featuring Michael Blonsky and Jeff McGuire. Again, it'll be at 10 a.m. Mountain Time, and it'll be on November 12th. We'll send out registration as the time gets closer. But thank you very much for joining us all today, and with that, we'll give you guys a little bit extra time. Have a wonderful day.